The bonding in metals. So the bonding diagram for metals, you should draw some positive ions in a lattice. These are positive ions, put positive charge in the middle of them. And then there is what we call a sea of delocalized electrons, all surrounding these positive ions, so in all the gaps. And even in the middle here. Okay, so the bonding model goes positive metal ions surrounded by a sea of delocalized electrons. So there's attraction between the positive ions and the electrons. So this would be fine for sodium. However, if we were to be very correct and we drew magnesium, we'd have to have the same positive ions, except because magnesium is in group 2, it forms 2 plus ions, so therefore the charge on the metal ions would be 2 plus, and you would have more electrons in the sea of delocalized electrons. So 2 plus charges on these circles. And then more electrons around the outside. It's quite hard to represent the electrons. Okay, so for magnesium, so for magnesium, then the ions have a 2 plus charge. There are more delocalized electrons. However, usually if you are asked to draw a diagram of the bonding in magnesium, it would be okay to just write the 1 positive charges rather than the 2 positive charges. So let's have a look how this relates to properties. So all metals have a high melting point. They're all solids at room temperature apart from mercury, and the reason behind mercury being a liquid is very complicated. So we need to explain the high melting point using the bonding diagram. So we need to, if it's a high melting point, then it must mean that these are strong attractions. So strong, electrostatic, attraction between, and this is where it's important not to get mixed up with the ionic definition, because it's between the positive metal ions, and the sea of delocalized electrons. Therefore, it requires lots of energy to overcome these and melt the metal. Electrical and thermal conductivity. So in both cases it's the delocalized electrons that are important here. So let's deal with the electrical conductivity. So the C of delocalized electrons are able to move throughout the metal structure so they flow and carry the current. For thermal conductivity, it's the same reason basically. So the C of delocalized electrons are able to move throughout the metal structure and carry the heat. And carry the thermal energy. That's a more correct way of writing it. Okay, so metals are malleable, and that means that they can be bent into shape. So the C of delocalized electrons allows the layers of metal ions to slide over each other once that has happened, the metallic bonds reform at the same strength. So the item is just as strong as the metal was before.